here we are again, re-recording Lecture 7, Part 1 of Engineering 101 2016. So what we talked about in the previous lecture was using signed binary and some of the logical operations, as well as a little bit of an introduction to little man computer. But I wasn't super clear in that lecture on exactly what I meant by signed and unsigned binary. So by unsigned binary, I mean the binary we have been talking all the way up until the last lecture. So I mean binary that only encodes positive numbers. When I talk about signed binary, I mean binary that can also encode negative numbers, and usually that means 2's complement notation. So just as a reminder, if I want to write positive 5 in unsigned binary, it is 0101, and if I want to write that in 2's complement binary to figure out what negative 5 is in 2's complement, to figure out what the negative equivalent of that is, I do 2's complement. So I flip the bits, 1010, and I add 1, so I get 1011, and that in 2's complement is -5. Okay? Let me know if you're interested in more examples, and I can actually go through some worked examples on my whiteboard here. Now I know how to do these recording things. But today's topic is much more interesting. It's talking about the little man computer, the first kind of real world application of all this binary computer architectural stuff we've been talking about up until this point. And like I mentioned in the previous lecture, it turns out we don't actually need anything more than what we already know to come up with this idea of a computer. So if we go straight into the little man, he has 5 basic components: addressable memory, a calculator with a register, like a display. Oops, sorry, I dropped my pen. A display where he records his information because he has no memory himself, 2 input and output registers where he can get in information or give out information, a program counter, keep track of where he is, and of course the tiny person whose job it is to run around, do all the things that the addressable memory tells him to do, and convey information from one place to another. And that statement, that he conveys information one place to another, is the key to why he doesn't actually need to exist inside a computer at all, but he's still a very, very useful conceptual tool to understand why your computer works in the way that it does, why it processes things in this way. So first, let's take a closer look at this addressable memory, because that's really going to be the cornerstone of this entire process. So when I say addressable memory, what I mean is a physical location. So I'm talking about a place. If you remember back from lab number 1, we had RAM, had the random access memory chips that you pushed into your computer. They were probably the hardest bit to get working. They usually are in that first lab. And on them they have a number of physical locations where information can be stored. That's what I mean by addressable memory. So what you can see on the right hand side of the slide is that I have an address, and it will have some value associated with it, and I can start from 0, and for the little man computer we say he has 100 addresses. They go from 0 all the way up to 99. Now in a real world computer you have many hundreds of thousands of potential memory addresses, and they won't be written, I sounded like Scooby-Doo there, they won't be written in ordinary numbers like this. They're actually written in hexadecimal notation for reasons you can figure out on your own. And you can see them in your C code if you like. But the important part about the memory is that each address has matches with one and only one value. We call that a cell. So anything in that value column there, each address only has one cell associated with it, and that cell contains a value. That value can only have a limited length as well, and for this little man computer we've said the length of that value can only be 3 digits. It can't be any longer than that. The important part is that the cells can store instructions, data, and programs for the little man computer. So if you remember the little man computer cycle, the first thing he does is he goes and he checks his program counter. Whatever number is on the program counter, he then goes to that memory address, gets the value for that memory address's cell, and then does whatever that cell's instructions tells him to do. We'll come back to exactly what those mean in a moment. But we can fill all of those memory addresses up with physical instructions. So let's say I write a really simple program for my little man. To do that, all I need to do is put a certain series of numbers in the addressable memory. Why? Well, because the little man always starts with his program counter at 0, the very first thing he's ever going to do is go to memory address 0 and get the very first value out of that. So in this case, the first value he'd get out of addressable memory would be 901. In our version of the little man computer, which is consistent with the Wikipedia version, but not always consistent with older versions, 901 means go and check the input. Remember how we have an input and an output register? That means our little man wanders over to the input and he checks the value that is in the input. He copies whatever that value is, doesn't delete it, he just copies it into his calculator. He copies it onto the screen of his calculator, because again, he has absolutely awful, non-existent short-term memory, so he puts it into the calculator. That's what we talk about as the result register. So 901 tells him to go over to the input, copy whatever number is there into his calculator, and that's it. Then he goes over to his program counter, he increments it, goes to sleep, wakes back up, checks his program counter again, now it's at 1, and he goes to his memory address, number 1, because now his program counter is at 1, and he gets his next instruction, which in this case is 312. 312 is an instruction which is store, that tells him to get the whatever is on the screen of his calculator and take it to memory address number 12 and store it there. So how does he know that 312 means that? So what we are physically doing is we're going to go through, and you'll do this in assignment 3, and write a whole bunch of what's called assembly code for the little man, and that will be transformed into these numerical instructions to encode operations for the little man to do. So let me give you some examples. If I wanted to get the little man to simply repeat a number that he received from the input, this is the code I would give him. So I know this is human readable machine code, but it should actually say assembly code, because this is literally assembly code. Imp out halt is little man computer code. These are instructions for the little man. Imp means go and check the input, copy whatever was in the input to your calculator. Out is the opposite. It's copy whatever is in your calculator onto the output. Halt is stop. That's it. Unfortunately, the little man doesn't understand these instructions. While they're pretty simple, they're still too complicated for him. The little man only processes binary instructions. So we need to know, how can we convert these into a binary form, into a form he can understand? And the answer is using those numbers we used before. So the code you see on the left hand side here, that is assembly code. The code you see on the right, that's machine executable code. So it's converted from a human readable form of instructions into a machine readable set of numbers. These sets of numbers are often referred to as OpCodes, or operational codes, and every different main CPU architecture has their own unique OpCodes. So you can see three examples here. 901, that's our OpCode for the little man to go and check the input. 902, that's our OpCode for the little man to take whatever is on his calculator and write it to the output. 000, that is our OpCode for the little man to stop whatever he's doing. Okay, that's our halt process. But he can do much more interesting things. Oh, the final thing I should mention, just let me go back, is that the line numbers for the assembly code end up being the memory addresses for the opcodes. So you can see imp is at line 0, input is at line 0, that ends up in memory address number 0. That's why he will do that first. Out, that's at line number 1, that ends up in memory cell number 1, and that means he will go and check memory cell number 1 second, and so on and so forth. So if we want to do something more complicated, we can use these two other commands called store and load. Store is a command for the little man, and he takes what's in his calculator and stores it at a particular memory address. Load is the reverse process. So he goes to a particular memory address and he gets some information back from it. And the reason we end up with these 3-digit operational codes is that they're not a 3-digit number. They look like it, but they're not. The first number is the operation, 3159, and that number tells you what to do. The last 2 digits tell him where to do it. So let's say we want him to store whatever is in his calculator at the moment at memory address number 12. we give him the number 312. 3 because it means to him store the information, and 12, 12, that's the memory address location where he stores it. Let's say we want him to retrieve that information later on, we'd use load 12 or LDA 12, and that converts to the number 512. 5 is operation load, and 12 is go to memory address number 12 and get whatever is there back, copy it back into your calculator. So if we want him to do something more complicated, like let's say adding two input numbers together, here is what our assembly code might look like. You can see we've got an input, then we store the value, then we take another input, and then we've got this add command. And add is pretty self-explanatory. Add means go and find whatever it is at memory address number 12 and add that to whatever is currently in your calculator. So if you want to see the opcode equivalent of this, here it is. 901, which is check your input, 312, store whatever is in your calculator in memory address number 12, that's what the 3 means. 901, check the input again, 112, 1 is the operation add, and 12 is add whatever you find in memory address 12, 902 is output that, and halt is stop. So hopefully you're getting the process now, that each of these individual assembly codes on the left hand side correspond to one and only one machine code on the right. Now we're running these machine codes in decimal. Real machine codes are not written in decimal. They're usually written, well, they should be written fundamentally in binary at a very, very low level, but we've kept them in decimal just to make them a little bit more readable than if we wrote them in this massive string of zeros and ones, but we could absolutely do that if we so desired. So if you're interested, the full list of little man computer operations is here. Why are we missing a few numbers? Well, it's because we've only got that first digit to give us an instruction. So from 1 all the way up to 9, we can only do 10 possible different instructions. Real little man computers, real opcodes, will actually be longer than just 3 digits because memory addresses are longer and we need to do more operations. So like x86 I think has 127 different operations rather than 10 we've got here, but it's exactly the same general process, and the ones we've told you about, add, subtract, store, load, break, input, output, halt, and dat or data, those are the core ones, and we'll hit some of the more complicated ones through next lecture. Long story short, don't bother memorizing those machine codes, those opcodes. You'll have to know that they exist, but these ones are just here to illustrate the general little man computer process. You should know how the little man computer process works, that cycle of checking the program counter, getting instructions from the memory address, doing those instructions, and incrementing your program counter. You should understand that this means everything in a computer is done sequentially, one line at a time, starting at the top and ending at the bottom, and you should understand that the little man computer, we can store both commands and numbers in memory. We usually put the little man computer commands at the beginning of memory because the little man computer's program counter starts them at 0, and we usually put data way down at the end of memory to keep them nice and separate. More on that in next lecture. So if you're interested in more, we've written up quite a detailed description of this whole thing. You can find it on the ENGR101 website there. And if you're interested in reviewing this content at a later date, you should be able to tell me what the components of a little man computer are, the importance of the program counter, and why we may not actually need the little man to do all this in the process. So we'll stop there for a moment and check back later if you want to see the second part of this lecture.